Okay, let's dive right into this explainer. We're going to take a familiar, profoundly relaxing everyday item and completely flip how you look at it. You know the routine, right? You run a hot bath, drop in a colorful sphere, and just watch it fizz away while you unwind. But underneath that soothing exterior, there's actually an incredibly precise, highly energetic sequence of microscopic events unfolding. Today, we're unpacking the molecular mechanics of bath bomb effervescence.
Think about it like this. A bath bomb is essentially a miniature, beautifully packaged chemical reactor. When you drop that sphere into the water, you aren't just making your bath smell nice. No, you are actively triggering a rapid chemical reaction. It's a calculated spectacle of physics and chemistry, meticulously designed to release scents, colors, and skin-softening ingredients all at once. To really grasp how this whole shebang works, we've got to strip away the pretty colors and look at the raw mechanics hiding inside.
So, let's start with Section 1, the core chemistry and the acid-base reaction.
All right, when they're dry on the shelf, these powders sit together indefinitely. Why? Because their molecules are literally trapped in a solid crystalline structure, completely unable to interact. On one side of the ring, we've got sodium bicarbonate. That's your mild chemical base, commonly known as baking soda. On the other side, citric acid, which is a weak organic acid usually derived from citrus fruits. In their dry, powdered form, they are completely inert. They're packed incredibly tightly against one another, but because they're locked in those dry, solid crystals, their molecules just cannot move to interact. It's basically a state of suspended chemical animation.
Now, since they're totally dormant on the shelf, we have to ask, what actually sets off the reaction? If these two highly reactive components are just sitting there staring at each other in a solid state, what's the secret key that unlocks their chemical potential and turns a quiet powder into a roaring, fizzing reactor?
Well, enter the water. It's the inciting incident, the ultimate catalyst here. The exact moment that bath bomb breaches the surface of your bathwater, those crystalline prisons dissolve. Suddenly, the molecules are no longer locked in place. They break apart into free-moving ions, swimming through the liquid. And honestly, that is when the microscopic chaos truly begins.
Let's look at how this chemistry actually builds. The freed hydrogen ions from the citric acid aggressively attack the carbonate ions from the baking soda. When these two collide in the water, a super rapid chemical exchange happens. They reorganize themselves, creating water, a byproduct called sodium citrate, and the absolute star of the show, carbon dioxide gas. This newly formed CO2 is literally the breath of the bath bomb.
Now, because gas takes up drastically more volume than a solid or liquid, the thousands of newly formed CO2 bubbles desperately try to escape the water, causing that intense bubbling. Imagine millions of microscopic balloons inflating all at once inside a dissolving solid sphere. The pressure builds instantly, and the gas forces its way out into the surrounding bathwater and up to the surface. This rapid, desperate escape of carbon dioxide is exactly what we perceive as the intense fizzing effect.
Moving right along to Section 2, Physics of the Fizz, Effervescence and Propulsion.
Effervescence doesn't just look pretty. It literally acts as a built-in motor for the bath bomb. On a microscopic level, those expanding and bursting carbon dioxide bubbles are violently energetic. They displace water rapidly, sending out tiny currents and microscopic shockwaves. And when you've got thousands of these happening every single second, it generates a massive amount of kinetic energy. This continuous propulsion is exactly what prevents the bath bomb from just sinking into a sad, mushy pile at the bottom of the tub. The escaping gas acts just like a thruster on a rocket. Because the gas escapes from different sides of the dissolving sphere at different rates, it causes the bath bomb to spin, roll, and dart across the surface of the water. This built-in motor is an absolutely crucial piece of engineering. Without it, that dense powder would drop like a rock and sit uselessly underwater. Instead, it moves, ensuring that all the amazing ingredients locked inside are evenly distributed throughout your entire bath.
Which brings us to Section 3, the sensory show, the supporting ingredients.
Okay, the chemical reaction gets the thing moving, but let's be real. Nobody buys a bath bomb just for a chemistry lesson. Let's look at the supporting cast of ingredients trapped inside that solid sphere, just waiting for the motor to disperse them. Now, manufacturers face a really tricky problem. How do you pack these dry, highly reactive powders into a tight sphere without setting them off? The answer? Using non-water liquid binders. They spray a tiny amount of witch hazel or alcohol onto the powder. Because water is the ultimate catalyst, if they used it to bind the shape in the factory, it would trigger the reaction right there in the mold. By using specific non-water binders, they can compress the bomb tightly while keeping the chemical reactor completely dormant until it hits your tub.
Trapped inside that solid structure are potent aromatic oils. As those carbon dioxide bubbles aggressively burst at the surface, they act like a dispersal system, literally launching a fine mist of essential oils into the air. This is exactly why your entire bathroom instantly fills with scent the second the fizzing starts. The mechanical action of the bursting bubbles is physically throwing microscopic particles of eucalyptus, lavender, or vanilla straight up into the air you're breathing.
But what about the stuff meant for your skin? Bath bombs often contain rich coconut oil or shea butter. Since we all know oils don't mix with water, the fizzing engine physically breaks them up into tiny, moisturizing droplets. Instead of clumping together in one spot, the violent effervescence ensures these microscopic droplets float evenly right on the surface of your bath. This guarantees that when you step into and out of the water, that even layer of oil coats and moisturizes your skin perfectly.
And here is how that famous bath art is actually made. Highly concentrated water-soluble dyes, known as lakes, are layered into the bomb. As the motor spins the sphere around your tub, these different layers dissolve at varying rates. It basically turns the bath bomb into a spinning paintbrush, leaving vivid, swirling trails of vibrant color across the surface of the water. It creates that incredibly satisfying visual spectacle we all love.
Now, if you just mixed pure citric acid and pure baking soda, the reaction would be incredibly brief, violently exploding and completely dissolving in like 30 seconds. To fix this, manufacturers add vital chemical buffers like Epsom salt or cornstarch. These act as fillers that physically get in the way of the acid and base molecules, slowing down how fast they can find each other in the water. This deliberate bit of engineering slows the reaction down so it gracefully fizzes for 3 to 5 minutes, perfectly extending the sensory experience.
All right, let's wrap this up with Section 4, the complete life cycle.
This perfectly maps the entire journey we've just talked about. First, we have the solid state, where the dry acid and base crystals are locked in their dormant, tightly packed sphere. Second is activation, the exact moment water acts as a catalyst, dissolving the crystals and freeing the ions. Third is the fizz, where the hydrogen and carbonate ions aggressively collide to generate rapid carbon dioxide gas bubbles. And finally, the dispersal, where the immense pressure of that escaping gas propels the bomb around the tub, perfectly distributing a payload of colors, rich oils, and perfumes.
It really makes you wonder, doesn't it? What other incredible, microscopic scientific events are disguised as everyday household items? What looks like a simple tool for relaxation is in reality a triumph of chemical engineering, physics, and sensory design, perfectly balanced to trigger right before your eyes. Keep an eye out around your home, because the world of molecular mechanics is always working right beneath the surface. So next time you drop a bath bomb, ask yourself, what other invisible chemical reactors are hiding in your home?